We're going to talk here in section 3.1 about derivatives of powers and polynomials. We're going to first learn a couple of rules that apply to derivatives. So the first rule is that if you have a constant times a function and then we want to differentiate it, that's what this symbol means. It's like applying this operation of differentiating to what's inside the bracket. So we're differentiating or taking the derivative of a constant times f of x. And our claim is that the constant just passes through. So it just is kind of inert through the whole thing. It doesn't go to zero. It doesn't add anything else. It's just a constant times the derivative of the function. And the reason, if this hopefully makes sense, is our definition of derivative of a function is going to be the limit as h goes to 0, and we would go c, that constant, times f of x plus h, minus we get c times the constant f of, or the function f of x all over h. And so that c, we could just factor out, and we could actually factor it all the way outside of the limit altogether. And so it would then become just c times that limit as h goes to 0 of f of x plus h minus f of x all over h. And hopefully we recognize that this is what we call f prime of x, the derivative function. So for example, some examples of this, let's see what that looks like in practice. If f of x is 5x to the third, and we want to find f prime of x, that 5 just hangs out. We then differentiate x to the third using our power rule, which is going to be 3 times x to the 1 smaller power, and so that's just going to be 15x to the second. Similarly, if we have, say, g of x is equal to pi times x to the first, then its derivative, g prime, is going to be the pi just hangs out. And remember, the derivative of x to the first is going to be 1x to the 0. That is just going to be just 1, and so our derivative is just pi. The derivative of, say, h of x is equal to x to the e. What a strange looking function. Remember, e is just a number, so that h prime of x, the e in front is going to just hang out there. When we differentiate x to the e, that's going to be ex to the e minus 1. Right? We bring the exponent out in front times x to the exponent minus 1. So that's going to be e squared x to the e minus 1. Crazy. And if we do something like now, if we had j of x is equal to 3 to the x power, now that's no longer a polynomial. So j prime of x, we do not know yet. We're going to have to wait before we can get an answer to that. Even stranger than that would be something like k of x equals x to the x. And its derivative, k prime, we're not ready to talk about that yet. So stay tuned. We'll have to come back to that at a later time. So we have to learn a little bit more first. Now, sums and differences, we also have a rule. So that how to take the derivative of a sum or a difference of two functions. So our rule is that the derivative of, say, a function f of x plus another function g of x, and that could be a minus as well, is going to be just the sum or difference of those individual derivatives. So we just differentiate each of those functions, and whoops, I didn't mean to make that a minus. Since that was a plus, that's also a plus. I don't want to confuse the issue there. So let's see what it looks like in practice. Here's f of x equals, say, 7x to the third minus 4x squared plus 5x plus the square root of 7. So f prime of x is going to be, well, these are a bunch of separate functions that are all being added or subtracted. So we're just going to take each derivative on its own, and we get to use the power coming down and multiplying that constant. So remember, the 7 just hangs out, but it's going to get multiplied by that 3 from the power rule. so that will be 21x to the second. In a similar fashion, we'll get a minus 8x. The 2 comes down and multiplies the negative 4. We subtract 1 from the exponent. 5x becomes the constant 5 because we subtract 1 from the exponent x to the first, which becomes 0. And remember, we said square root of 7 is just a constant, so its derivative is 0, and that is our answer. Now remember that our power rule applies to all powers of x. So the power rule applies to all powers of x. So in particular, let's revisit some of these ideas we talked about before, but now in a little different context. So if we say f of x is equal to x to the 3/5, we talked about this before, if you remember, when we have an exponent that is odd over odd and between 0 and 1, if you remember, that was supposed to give us a vertical tangent. Well, let's see why the derivative is, why that's going to have a derivative that is a vertical tangent. Struggling to spell vertical tangent here. There we go. So f prime of x, we're going to get 3/5 x to the negative 2/5. So I'm going to write that as 3 over 5 times the 5th root of x squared. So the claim is now that the graph of this thing is going to look sort of like a cube root in a way. So imagine that this is doing something like that. And our claim is that right here at 0, that tangent line is going to go straight vertical. We can see that here algebraically because as we plug in values of x that get close to 0 from the right, that as you get a very small positive number, the squaring it's going to keep it positive, and 5th root, if this is very, very small, like say 0.0001, this denominator is going to be very, very small. 3 divided by a very small positive number is going to go to positive infinity. That is, as we look at tangent lines coming in from the right, they're falling off the cliff and going to straight vertical, which that undefined slope we can think of as a slope of positive infinity. As you come in from the left and you use numbers that are approaching 0 but negative from the left side, it doesn't matter that they're negative because when you square it, it's still going to be positive. So you're going to get a positive 3 over a very small positive number. So as you come in from the left, those tangent lines are still positive and they go to straight vertical. So the slope goes to positive infinity from both sides. That leads to a vertical tangent. So if we have something like, say, g of x is equal to x to the 4/5, remember we said even over odd, where that is between the exponents between 0 and 1 is supposed to be a cusp. So let's see how we can tell it's going to be a cusp from its derivative. So using the power rule, we're going to get 4/5 x to the, subtract 1 from 4/5, we get negative 1/5. That's going to be 2 on top, 5 on the bottom, and we're going to get the 5th root of x. So now the claim is our graph is going to look something like this. There's our cusp. So as you come in from the right and you look at those slopes of the tangent line, it's positive, 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 fall off the cliff, go to positive infinity coming in from the right. Now you can see that algebraically, if you plug in a very small positive number, the 5th root of a positive is still positive. You're getting something that is not 0 over something very, very small. That is going to go to positive infinity. But when you come in from the left, now you see negative slope, bigger negative, fall off the cliff. The slope is going to go to negative infinity. And you can see it algebraically if you plug in a number that's approaching 0 from the left and you put in a very small negative number, the fifth root is going to make that a very small negative number. A positive 2 divided by a very small negative is going to go to negative infinity. So that's the algebraic understanding of why x to an even over odd power, when that exponent is between 0 and 1, is a cusp. Okay, and we also had, say, h of x is equal to the square root of x. This we said was a restricted domain. So we know that the domain of the original function h, the domain is going to be x greater than or equal to 0. But when we go to take its derivative, so we're going to think of this as x to the 1/2. So when we find its derivative h prime, we get 1/2 x to the negative 1/2, which is otherwise known as 1 over 2 square root of x. Now in this case, as x approaches 0, we see that because of the radical, x has to be greater than or equal to 0, but because it is also in the denominator, it cannot equal 0, so we have to take away that or equal to part. So its domain is going to be x strictly greater than 0. So we said earlier that when you differentiate, you cannot gain domain. So we do not gain domain by differentiating. But sometimes differentiating, like you can read that writing anyway, we do not gain domain by differentiating. But sometimes we can lose some. So we lost 0 in this act of differentiating. So I'm going to say we sometimes lose some domain. Can't gain domain, but you might lose some. Okay, so let's go to a new panel here. And let's talk about looking at a couple of these graphs. We're going to say f of x is 1 over x. We know that the graph, we hope we know, the graph of 1 over x looks something like this. It's got a vertical asymptote of x equals 0 and a horizontal asymptote of y equals 0. So if we take its derivative, let me change colors there. So let's go with f prime of x. So we can think of this 1 over x as being x to the negative 1. So its derivative is going to be negative x to the negative 2. That's going to be negative 1 over x squared. Now you may or may not remember, but the derivative of the graph of 1 over x squared would be our volcano graph, and negative 1 over x squared will reflect that in the x, so we're going to get something that looks like this. And something to note that will come up somewhere along the way, the spacing here between the y-axis and the curve will get bigger as you differentiate. Okay, so the spacing here is going to be a little bit wider than it was in the original. And then if we go even further, and so now we're going to say, let's take the derivative of that. So let's find our second derivative. That's going to be the derivative of our first derivative, and we can think of that back in as negative x squared. Then that's going to be the negative 2 times negative 1 will be positive 2. X to the subtract 1 from the exponent will be negative 3, which could also be written as 2 over x to the third. Now, interestingly enough, if we go to graph this, the 2 over x to the third, now what happens is it's going to look kind of like 1 over x, in that it's going to be positive in quadrant 1, and it's going to be negative in quadrant 2. Now, again, what we're saying, though, and what you'll see is that this distance between the curve and the y-axis gets bigger. So this distance will be a little bit bigger than this distance was, and that distance is going to be bigger than the distance was there. So each time you take a derivative with a vertical asymptote, it goes a little bit further away. You can also see evidence of the odd and evenness of these power functions. So you can see that when we had x to the negative 1, that it was going to be up here in quadrant 1 and quadrant 3. It was going to be symmetric with respect to the origin. If you double reflected that or rotated it 180 degrees around the origin, the graph would remain the same. When we got to an even power, negative 2, it's going to have symmetry in that line x equals 0. And then back to another odd power here, and we're back to symmetry in the origin. So that's still holding true even with negative exponents there. Okay, let's try another derivative question here. Let me get a white color to start with. So we're going to say f of x is 5x to the 7th minus 4 times the 4th root of x to the 3rd minus 4 over x plus pi times x minus e to the pi. Whew, there's a question for us. Let's see if we can find its derivative and sort that out. So let's find f prime of x. So using our power rule, the 7 will come down and hit the 5. That's 35. We'll subtract 1 from the exponent. That's going to be 6. Now we have this 4th root of x to the 3rd. I'm going to calm off to the side here for a minute and know that the 4th root of x to the 3rd we can write as x to the 3/4. So that derivative of minus 4 x to the 3/4 is going to become the negative 4 times the 3/4 x to the subtract 1 from the 3/4, and so that's going to be negative 3 x to the negative 1/4, which you're fine leaving like that, or if you'd rather, you can call it negative 3 over the 4th root of x. Now the next one, now we got this 4 over x, we're going to run off to the side over here, and for derivative purposes, we want to think of that as 4x to the negative 1. So its derivative, we're going to take the exponent times 4, that'll be a negative 4. We'll subtract 1 from the negative 1 to get x to the negative 2. So we're fine writing that as negative 4x to the negative 2, or we could, if we prefer, and we need to be able to go back and forth either way, write that as 4 over x to the 2nd. And then we have now, that's a funny constant pi times x. Its derivative is going to be just pi. The next one looks daunting, but recognize that e is just a number, pi is just a number, so e to the pi is just a number, and the derivative of a number is just 0. So let's take a look at some tough ones here. These are going to take some kind of clever strategies. So we'll give you f of x is equal to 3x to the 2nd plus 5x minus 4 all over x. And then we'll talk about g of x, which is equal to 3x minus 4 to the 2nd. And then we're going to do h of x, which is the square root of x, times 3x plus 1 over x. Now in each of these we want to find the derivative, but we don't at this point in time know how to differentiate something that's a quotient that has a division. We don't know how to differentiate something that's got a function to a power, nor do we know how to differentiate something that's two functions being multiplied. So since we don't know how to do those yet, then we have to instead do some algebra up front. So we can split this up and call it 3x squared over x plus 5x over x. I'm not doing any calculus yet. Minus 4 over x, which after we simplify will be 3x plus 5. And then for derivative purposes, I'm going to write the over x as x to the negative 1. That's still f of x. But now we have maneuvered it to where it's going to be a pretty straightforward derivative, hopefully. The derivative of 3x is just 3. The derivative of 5 is 0. The derivative of negative 4x to the negative 1 is going to be a positive 4x to the negative 2. That works, or you can rewrite that without the negative exponent. That's your choice. Now the next one, again, we're going to have to do some algebra up front first. So we're going to square that out. That's, remember, first one squared, twice the product, plus the second one squared. Now it's pretty routine, hopefully, or it's getting routine. That's going to be 18x minus 24, and the derivative of 16 is 0. That's our derivative. And the last one, the h of x, this blue one, we're going to have to, distribute that square root of x. Now we're going to think of that as x to the 1/2. So I'm going to try to get some space here. And not going to let me erase, so I'm going to work below it then. So x to the 1/2 times 3x is going to be 3x to the, we have to add exponents, and that's going to be 3/2 power. This 1 over x we're thinking of as x to the negative 1. So when we multiply x to the 1/2 times x to the negative 1, we're going to add those exponents and get an x to the negative 1/2. That's still just h, but now we're in a good position to take the derivative. So we're going to get 3 times 3/2. That exponent comes down. X to the subtract 1 from 3/2, we'll get 1/2. Then we'll get a minus 1/2. We bring that exponent in front. Subtract 1 from the negative 1/2. That's going to be the negative 3/2 power. And that will work for our derivative. Very good.